in this part of the workshop, we are going to look a little bit at how we can process the 4D STEM data sets that we collect in digital micrograph. Before I go into the software, I have a couple of slides just to make sure that everyone is on the same page and we have all the background that is needed before we go and process the data. And here's my email address. If anyone has any questions, please, besides submitting your questions here, you can contact me anytime in the future directly, no problems. So we talked about what 4D STEM is. So as you saw during the experiments that Roberto just showed us very nicely, at each probe position in a two-dimensional scan, we collect a two-dimensional diffraction pattern, and that's why this is commonly now called a 4D STEM experiment. So you have 2 dimensions diffraction and 2 dimensions scanning the sample. Now, the product that Gatan offers for 4D STEM is called the STEMX. And STEMX is an add-on that gets added on top of our cameras. So here are some of our cameras that you can see. The K3IS and OneView-IS is what Roberto was using this morning on their grand arm. We also have another camera called the Rio, and also announced another camera, a hybrid pixel detector camera for diffraction imaging called Stella, just last month. So with these cameras, you can do regular TEM experiments, diffraction imaging, in situ microscopy, and tomography. And with the STEMX, you add the 4D STEM capability to your existing cameras. And what that means is you can do applications like strain mapping, virtual imaging, differential phase contrast imaging, orientation mapping, and many more different types of applications. And as we discussed and we saw, you use the STEM-SI acquisition technique in digital micrograph to set up your experiment. So here, for example, you can see seabed is selected, and you set up your 2D array size. So this is the number of pixels, the step size, the pixel dwell time, and you click on capture. When you click on capture, then the digital micrograph takes control of the experiment. It starts with the camera taking a diffraction pattern. The diffraction pattern is stored. At the same time, you can also collect other signals if, for example, you have the HADF detector inserted, if you have EDS being collected at the same time. If you have a cathode luminescence holder, you can collect a CL signal. Once the diffraction pattern is captured, a signal is sent from the camera through the STEMX box to the DigiScan, and the DigiScan moves the probe position to the next pixel. And the same thing happens again and again and again until you cover the full area that you have selected here in the site acquisition window. So the camera is going to be the timing master, and we do this via hardware synchronization. So we collect 4D STEM data sets at the speed by which you have selected to run the camera. So depending on which camera you have and how fast that camera can be operated, that defines how fast you can collect your 4D STEM data sets. So that was, for example, the difference between the OneView, where you can go from 25 frames per second to 300 frames per second if you go from bin by 1 to bin by 4, versus K3IS, where you can go from 150 frames per second all the way up to more than 3,500 frames per second by reading out different areas of the sensor. Reading out smaller sub areas gives you a higher frame rate with the K3IS. Once you have collected your 4D STEM data, you can go into digital micrograph, and we have implemented software and workflows in DM for virtual imaging, strain mapping, and DPC. A couple of other things to point out is you can also do with Gatan equipment on the same sample at the same microscope session other types of experiments. So you can collect different types of data sets to complement the experiment that you're running. You can, for example, start with spectroscopy. So if you have a spectrometer, and then validate your results using 4D STEM. So that is shown on the example here on the left-hand side. Or you can go the other way around. If you have done some 4D STEM experiment, for example, here is a strain mapping experiment, you can look at the chemistry using spectroscopy and yields and understand what is happening at the interface in this example, for example, in your sample and why you see the phenomena that you see from the 4D STEM experiments. So that's one advantage. Another thing, a couple of questions there were if the K3 camera that we are using here is installed on a Gatan imaging filter or not. So what you saw today was a pre-GIF camera, so it is not on a filter. But if you do have a K3 on an imaging filter, then you can apply a filter and look at a zero loss filter diffraction pattern, which has, as you can see in comparison between unfiltered and filtered diffraction patterns here, higher signal to noise ratio and better definition of the features in the seeded pattern. So you get higher quality diffraction patterns and as a result, better studies on your experiments. And then the other thing is being able to do 4D STEM in counting mode. So that was the difference between the OneView camera and the K3IS camera. This slide is generously again provided by Roberto on the same microscope, same sample, exact same microscope conditions. You can see the difference in a signal to noise ratio between a OneView camera, which is a scintillator-based camera, versus a K3 camera, which is a direct detection counting camera. So again, if you have samples such as moths and coughs that are very, very beam sensitive, you are going to need a high DQE, high sensitivity, high signal to noise ratio counting detector to do your 4D STEM experiments, because you need to reduce your beam current to protect the sample, but at the same time, you need to be able to collect enough signal in your diffraction patterns to be able to do the analysis. Okay, so as I said, we can do 3 types of analysis, and I'm going to show you in DM. The first one is strain mapping. And the way it works, I kind of referred to it during the live demo on the microscope, is that we compare the diffraction patterns that we collect in nanobeam mode in a strained region of the sample to diffraction pattern in an unstrained region of the sample. So you generate a reference diffraction pattern from an unstrained region of the specimen, and then you compare pixel by pixel the rest of the diffraction patterns in the data to this reference diffraction pattern and measure how much the distance between the reflections have changed. And the distance between reflections in the diffraction pattern is inverse to the d-spacing of the crystalline planes. And if the d-spacing has changed, it means that you have strain. So that is how you measure the strain in your sample. The other one is being able to do virtual imaging. You saw this figure from Roberto. I have the reference down here. So the nice thing with doing using virtual apertures is that you can do things that maybe not possible to do physically. So designing virtual apertures that are not possible to physically make. And then you also don't have to spend a lot of time on the microscope thinking what kind of conditions you need to use to be able to extract the information that you want from your sample. You just collect one 4D stem data, and then you go and process it offline. So if you are on the real space image, you can have virtual selected area apertures and generate the diffraction patterns from those selected regions. So these would be virtual selected area diffraction images. And if you go to the diffraction domain, you can do the same, apply virtual objective apertures and generate your virtual bright field and dark field images. And I'll show you how we do that in digital micrograph. And the third the third type of analysis that we're going to look at is differential phase contrast imaging. So as you can see in this cartoon here, if you have an electric field in the sample and you have a thin enough specimen, as you pass through the beam is deflected. If you measure this beam deflection, you can calculate the electric field in the sample. So you collect your 4D STEM data set in a condition where you have a large convergence angle. You measure the center of mass shift, and then from this you can calculate the beam deflection and the divergence, and from these you can calculate the charge density and also the electric field in the sample. One more thing, I sent a couple of links in the chat. So we have several training resources on our Gatan webpage. We have a 4D STEM technique page. In the technique page, we have the strain mapping page where one of the examples that I forwarded the link for you to download is actually, I go step by step on how you can process that sample in this strain mapping page. And then we have several videos. So the demos that I'm going to show you in digital micrograph today, we have made short videos of how you can do each of these data processing in DM. So if you go to our media library, you can see those videos. And if you download digital micrograph, or if you have it already, then you can use these videos to help you process your data sets as well. Okay, so let's start. Yeah. Any questions so far before I go in DM? I haven't been looking at the question pane. Stephanie, let me know if there is anything I can address as I switch. Okay, so let's go to digital micrograph.
Yeah, so there's a few questions kind of asking a little bit more about strain mapping, but I'm guessing that you'll get to some of these things as you go through.
Okay,
we can come back to them later.
Sure, sounds good. Okay, so here is digital micrograph. There were a couple questions asking what version this is. This is GMS 3. I think the last version that we have released is 3.4, and that's what Roberto was using. On the left-hand side, you can see the display panel. You saw the microscope panel. I'm running this on my laptop, but it's in simulation mode. So you can see similar to what you saw on the microscope computer as Roberto was collecting the data. So you can interact with Gatan hardware as well as the microscope in DM. You can see we have different workspaces here. And on the right-hand side, we have the techniques. So depending on what licenses you have installed and what hardware you have installed, then you get different buttons here. We are going to focus on 4D STEM today. So that's the technique that I'm going to select. And you can see strain mapping and DPC, and we'll get to those. The first example that I'm gonna start with is this 4D STEM data set on a copper foil grain boundary. So this is a copper sample that that was just a planar sample that we thinned in a PIPS and put it in a microscope and collected the 4D STEM data with. You can see this is 4-dimensional data set. I have 45 by 45 by 512 by 512 pixels. And so the first thing you also saw Roberto use it quite a lot that I'm going to show you is a picker tool here. So spectrum imaging picker tool. If you have used our yields, you are very familiar with this picker tool. So you select the picker tool, you put it on your 4D STEM data set, and immediately it gives you a diffraction pattern from the selected pixel by the picker tool. So as I move from one grain to the other grain in this copper sample, you can see that the diffraction pattern is changing. So this is our grain boundary. And this is basically doing a virtual selected area diffraction from this specific pixel. And if I grab the corner of this picker tool and increase its size, now I am summing all the diffraction patterns in all of these pixels. And you can see the intensity in the diffraction pattern here increased. So this is, again, a virtual selected area diffraction pattern that I'm generating from these selected pixels here. And as I move the picker tool, it changes. Okay, so this is the first thing I wanted to show you. The next thing is you can see on the left-hand side here, I have the slice. And if I click on my diffraction pattern and select show range, you can see as I move this green box, which is selected by the slice, the sliders here on the slice move. And also the contrast here in the front image in the diffraction pattern changes. And if I change also the size of this green box, you can see the sliders move and the contrast changes. So somebody was asking earlier, what is the contrast that we see in the 4D STEM data front image? This is basically the selection made here by this virtual objective aperture. So if you move this aperture on different reflections, so here I am on the direct beam, so I'm getting a bright field image, and now I move it to this reflection, and I'm getting a dark field image from this grain. So because I have selected the reflection that is specific to this grain, this orientation, this one lights up. If I go ahead and move it to this reflection, maybe this one lights up. So this is one way to do virtual dark field, bright field imaging. And I brought up this slice by selecting show range here on the slice tool on the left side. Another way to do that is selecting drawing an ROI, and this ROI can be any shape. It can even be like a loop, so any random shape, and you can put multiple ROIs on the image. So let's say I do the same. I draw ROI on my direct beam, and then you go under SI menu, map, and then you go either signal or signal dynamic. If you select signal, it is going to give you a bright field image like here. If I now select, let's say, another ROI and do the same, but instead do signal dynamic, now I am going to get a dynamic image that is going to update as I move my selection around. Okay. So there we go. So this is another way to generate virtual dark field, bright field images. There is one more way that I like to show you, and that is using for example, one of the selections here, let's say a bandpass, for example. I put this on my diffraction image, and this will be similar to having an annular detector, if I can select that, on your, and doing this on the microscope, but now we are doing it virtually. So you can change the inner and outer angles. So depending on what angular selection you have, you will have a different type of image. You can have a hadaf, you can have a bright field, you can have an annular bright field, depending on the angle you have selected. So once you've adjusted your angle, you do the same thing. You go to SI, map, and signal. And now I have an annular as a virtual image from a virtual annular detector. And what DM does, it goes pixel by pixel in each of the diffraction patterns and sums the signal in the region selected by this bandpass. So that's how you generate your signal. Okay. Let me check my notes and see what I want to show you. I showed you the, okay. So because I'm just showing you the basics here, another tool that you have for 4D STEM data processing in digital micrograph is under the volume. Roberto showed you when you are collecting the data, there are multiple ways to reduce the data size. So you can either select binning on the camera, or in the case of the K3 sub area and binning on the camera. You can do further reduction under the STEM SI setup window. So that will be software reduction. As you're acquiring the data, it also bins them additionally before it stores them. But if you want to do so afterwards, also after you collected your data, you can do that here under volume. So you can rebin all of the 4 dimensions in your data cube. Another way to reduce your data is subsampling. You can do subsampling again in all of the 4 dimensions. I think it makes more sense if you do the subsampling in the spatial dimension. And another thing is this option for reordering. So the way when data is coming in from the camera, the way we store it is going to be the most efficient way to get the highest frame rate possible from the data. So it could be first the spatial dimensions and the diffraction dimensions, or the other way around. And when you want to do data processing, depending on what you're doing, if you need access first to the diffraction dimensions or first to the spatial dimensions, one or the other could be faster. So you have the option to rotate or reorder the data under the volume menu as well. Okay, that is what I wanted to show you. Yeah, I think that is it on this data set. So you have this data in the link that I sent you. And you can open this in the free version of software, and you can use the picker tool, and you can extract the images and generate some bright field, dark field images as well. Okay, so the next one, I'm gonna move on to strain mapping. So here is my, again, 4-dimensional data set. This is a sample made of layers of silicon, germanium, silicon, germanium, with increasing germanium content in the layers as we go from top to the bottom. And because there is germanium in the silicon germanium layer, in the growth direction, we expect to have strain. So let's see if we get that. For strain mapping, as I said earlier, we use the 4D STEM technique and go to the strain mapping window. And you just follow the workflow from top to the bottom of the strain mapping technique window. So again, the way we do this is calculate a reference diffraction pattern and compare the diffraction patterns in the rest of the areas of the sample to this reference pattern. And from that, measure the strain. Okay, so to do that, sorry, I wanted to show you one more thing. So if I put the picker tool on this data set now, you can see this is silicon on zone. As I move down, if I move up and down, you can kind of see that the diffraction pattern is breathing as I go over the layers with germanium. I hope you can see that with the refresh rate in Zoom, but that is basically telling me that, so the reflections are moving farther and closer, so there is some measurable strain. So let's see if we can find that.
Hi, Anna. Can you increase a little bit the window? Yes.
Okay.
I can see it.
Is that better?
Yep, that looks better.
Okay. So let's first, we have to tell the software where is the region of the sample that does not have any strain. So you use this on-strained area tool. You draw a box where you know there is no sample in the specimen. So I know in the silicon layer here, I have no strain. So I specify that region and I click calculate strain. Here, one important thing that I want to show you, and Roberto also referred to this kind of during the microscope session, is it is very important to know the angle, the calibrated angle between your diffraction pattern rotation and your scan rotation. So you want to know the growth direction corresponds to which reflection in your diffraction pattern and what is the angle between those. So in this example, I have measured negative 35 degrees. So when I measure my strain and I calculate the strain in the diffraction direction, it is going to rotate it then so that when I get the X and Y strain maps, I get them in the X and Y directions of the scan of the real space in the sample. Okay, so let's click on reference. So when you click on reference, it uses all the diffraction patterns in the unstrained area, and it calculates an average diffraction pattern, and it gives you a reference diffraction pattern. In this reference diffraction pattern, you can define the directions for which you want to calculate the strain. So those would be this U and V vectors. So you also identify the central spot. From the center spot selection, it is going to generate a template that is going to use to find all the other diffraction patterns in your data set, or the reflections. And as I said, so the U and V would be the directions for which I want to calculate the strain. U here, in this case, is the growth direction. And as you can see, this is about 35 degrees compared to the scan direction, the growth direction I have in my data set. And then the green circle defines how far out I want to go and how many orders of reflections I want to include in my strain calculations. If you have set up your camera length to include high signal to noise ratio reflections, higher orders, it is better to include them. But the software has a threshold in it. If it doesn't find enough signal to noise ratio in the reflections that it finds, it's going to ignore them. For now, to save time, I'm just going to make this small and move on. Okay, so once we define our directions, I click on calculate disk. And as I said, it is calculating a template that is going to use to find all the positions of the reflections. And now we are all set to do our strain mapping. One other thing, a couple other things, if you have collected a data set that in the region that you collected the data set, you do not have an unstrained area, it is possible to also collect data from a different region of sample that you know doesn't have any strain, calculate the reference from that data set, and then use that reference diffraction pattern and apply it to the data set that you know has strain. So you can do that selection here in this dropdown. So if I had other reference diffraction patterns, I could select those. The important thing is to make sure that the acquisition conditions, camera length, is all the same for these two data sets so that you can use the diffraction pattern, the reference diffraction pattern from the other data set for this data set. The other thing is if you are on the microscope and you want to do a quick analysis and you have collected, let's say with the K3IS, a 512 by 512 scan area, it might take some time to finish calculating the whole strain map. So you might want to do a sampling interval to, for example, skip every 5 pixels or skip every 10 pixels and calculate a quick strain map instead of calculating the full data strain map for the full data set on the microscope. So within minutes, you can do a quick calculation, get some answers and decide if, let's say you want to increase the exposure time, or you want to change the camera length, or you want to move to a different region of the sample. And then once you're happy with that, you can take that and process the full data set offline. For here, I don't have that many pixels, so I'm going to just click calculate. So DM is going to generate the strain, so the U and V vector maps. Those are used mostly if you want to do further analysis and write your own scripts. And also it is going to give me the strain in X, the strain in Y, the shear, and also the rotation. Okay, and you can see it is doing this quite fast. I have these actually colored here. So you can see from the top, we had the silicon region. I told you that we have increasing germanium as we go down, and you can see there's the strain increases. Here is showing you what is the range, the color. You can add this to the image if you go to layout and select add oh, let me delete this. Add intensity bar like that. And you can color your images if you right click on the image and you go to color and you select different color tables. I have selected temperature here. All right, so that is strain mapping on a nanobeam diffraction pattern in digital micrograph. Okay, so I am going to close this one.
While you close, I have a quick question, Hannah. So if you have two similar data sets, right? So one that is like unstrained and the other one is a strain.
Mhm.
Can you use them to compare, or the unstrained area has to be from the same data set?
No, it doesn't have to be. So but the imaging conditions for the two data sets has to be the same, but you can calculate the reference diffraction pattern from one data set, then select that reference diffraction pattern here under use, and then apply that to a different data set.
Okay, thank you.
Yep.
I have a similar question. So when can you talk a little bit about how you chose and designed your sample? So how do you select to make sure there's a strain region and an unstrained region, thinking about thickness, choice of sample? Can you comment on those parameters?
Uh, so okay, so the sample cannot be too thick, obviously. If it is too thin, then you get strain relaxation, so you will not, stress relaxation, so you will not be able to detect much. So I have people who actually make samples with different thicknesses, and they take it to the microscope and they measure their strain, and they decide based on the results what kind of a thickness works best for their type of analysis. I'm sure probably Roberto, you can comment. There are simulations for this as well.
Yeah, there's I can put the reference on that, and also in the same note, also the dose, right? So there's a limitation of
Yes.
the signal to noise that you need to calculate
Yes.
the strain.
Yes. Yeah.
And also, if you remember, like at the very beginning of my presentation, I showed two different diffraction patterns. One with less, like a thin area. The other one has more like features within the disc. So as Anna mentioned, there is a sort of like sweet spot that you have a better accuracy in the strain mapping. But yeah, so it does very thin sample. We might face some issues because of bending. So it has like some sort of like a minimum thickness, and depends on the sample too, right?
Yeah.
And then for the point maybe about having different areas of the sample, so one strained and one strain free. I don't know if the two of you wanted to talk about that as well. There's a couple questions.
So you probably should have some ideas about your sample when you go into the microscope. You can't just go blind so usually, for example, for semiconductor people, they know there is no strain in the substrate. One other thing, if you don't define an unstrained area in your sample, then DM is going to generate the reference diffraction pattern from the full data set, and then compare each of the diffraction patterns in each of the pixels to that reference diffraction pattern. So you kind of get a relative measurement of the strain in the whole region of interest instead of an absolute measurement when you are comparing this to an unstrained reference diffraction pattern. I hope that
Yeah, and there you
clarifies.
yeah, and that you compare to the mean, right? So that's
Yes.
your
Yes.
your reference lattice will be the mean lattice of the whole region. So
Exactly.
one just to add to that, during the demo, so I had a GSO as a substrate, right? So if I want to calculate the strain on the top layer, like the thin layer, I would use that as my reference. So that's just one of the examples, right? So if you do not have an example, you could use even like a simulated data set, for example, right? With this exactly the same conditions that you want to compare. Or if you don't have any reference, you could always refer to the mean, right? Like Anna mentioned there. But typically for that type of sample, like nice like crystalline samples with like reference, like semiconductor, for example, you probably find like a substrate or something that you can use as your reference lattice.
Okay. One other thing I forgot to show that I wanted to show on this data set actually is this one is actually not too bad. You can see as I move the beam, the 000 beam doesn't move that much. But depending on the magnification and depending on how STEM is set up on your microscope, and if you have these what is called D-scan or you don't have it on, you might see quite large movements of this direct beam as you move the picker tool from one region of the data set to the other. If you do collect the data set and then you go offline and you see that you have that that in your data set, before doing the strain mapping, it is better to take that out. And the way to do that in digital micrograph is you put an ROI on your 0 beam. So as I'm doing here, and then you move your picker tool to different regions of the sample and make sure that ROI is going to contain the beam as it moves. Again, in this example, it's not moving a lot, but if you do have movement, make sure that your beam stays in the ROI. And then you go to SI and you select align SI by peak. And this is similar, actually, algorithm to what if you have yield spectra, you would do align SI by peak in there. Here, instead of aligning the spectra, we are basically cross-correlating the selected regions in all of the diffraction patterns in the data set, measuring the shift, and then bringing back the diffraction patterns to the center. So if I click on align SI by peak, that is what it's doing now. So it's going pixel by pixel, finding the position of the central beam, and then doing a cross correlation and measuring how much shift it has been in the X and Y directions of the diffraction pattern. It is also gonna give me a cross correlation result. So this is telling you how well the cross correlation worked, and you can change in a tag. You can change what is if it is 1, it worked perfectly. If it's let's say I have set it to less than 75%, then it's gonna fail and it's gonna turn into red. And if I'm happy with this measurement, then I can say, yes, I want you to correct this data based on this measurement, or I can say no. Sometimes when you do these measurements, they don't, you have to look at the results and see if they make sense. And if they do, then you can apply that. My next data set is going to be for DPC. So I like to also mention that in DPC, especially for magnetic field measurements, what you are trying to measure is actually movement of the beam. So you have a large convergence angle, you look at the 0 beam, and you want to measure how much the beam is being deflected because of the field in the sample. So there are a couple of things to consider. First of all, you don't want to just go ahead and blindly do this SI alignment and take it out, because that might be from the sample. The second thing is you want to make sure that you are not taking microscope effects into your analysis. So what a lot of people usually do is actually collect 2 data sets. They collect one data set on the sample region where they want to measure the field, and they collect another data set on the vacuum. And they measure how much the beam actually deflects in the vacuum. And then they take that out of the beam deflection measurements in the sample area to make sure they are purely measuring the properties of the sample and not measuring the beam deflections because the scanning coils are not set up properly. Okay, so that is a good move into the DPC. So this data set now was given to me by Ensign folks for DPC measurements. So if I again do use the picker tool, you can see I have a diffraction pattern. So the two data sets that you saw earlier, they were on collected with the OneView camera. This one, it has been collected with the K3IS camera on the back of a Gatan continuum imaging filter. So this is a zero loss filtered diffraction pattern on a K3IS, so in counted mode. And so you can see we have a large convergence angle here. We are looking only at the direct beam. And as I move the picker tool, you can see changes in the contrast. And that is exactly what we want to measure. We want to see how much the beam, the center of mass of the momentum, how much it is changing as I go through the atomic columns in the sample here. Okay, so the way we do that is using this DPC technique here in digital micrograph. There are different ways you can do that. You can do a cross correlation. This would be more when you want to measure the beam movement. So I would say if you have magnetic samples, and you want to measure how much the beam is moving, the center of mass more, for example, similar to what I'm showing here. If you select center of mass, you can apply a mask diameter so that if you have some, I don't know, some noise, or you have other disks or other reflections here in your image, you can mask them off by applying a mask. And again, if you have measured your rotation, the diffraction rotation, you can apply that angle here. And that's, again, very, very important, as Roberto was saying in his presentation. You want to make sure to calculate in the correct directions. And here is what I was saying. If you do have a data set that has been collected in vacuum, you can measure the beam displacement in that data set and then apply that as you are calculating the beam displacements in your specimen area to make sure that you're purely measuring the properties of your material. Okay, so it's really simple. Once you have your data set, you click on measure beam displacement. And so it is now calculating the X and Y in the diffraction direction maps, center of mass movement in X and Y directions. And if I had put in a rotation angle, it would have given me these deflections being with that angle applied. And this color map that you're seeing is basically the vector map, the beam displacement vector map. And this color wheel is telling you the direction of the vector in this vector map. So once you have the beam deflection, you can calculate also the divergence. From the beam deflection vector map, you can calculate the electric field. And from the divergence, you can calculate the charge density in your sample. Okay, so here is calculating. Oh, I had the wrong image selected. So, and this is the charge distribution map. Now, another thing which I think is going to be, again, a good opening for the next session is these, whatever I showed you so far is what we have implemented in DM. So simplified, easy to use analysis tools for different types of 4D STEM data sets. But you have the possibility of writing DM scripts or Python scripts in digital micrograph as well. So let's say I move this to workspace 7. Let's say I have this beam deflection vector map. I can write a script, a Python script in DM, and from this vector map, I can plot a quiver plot as well. So this you cannot do. Plotting a quiver plot in DM is not that straightforward, but doing it with Python, it is very easy. So you can write your Python code and use that code to plot the quiver map that you need for your publication or presentation. So we have some basic tools for data processing that are quick and easy to use. And if you need to do more with your data, as you will see, Stephanie and Roberto are going to show you later today, you can also do that via scripting in digital micrograph.